Good afternoon, everyone. My name is Awad, and in the next 4 minutes, I'm going to share with you a line of research in our lab that's focused on the development and study of soft robotic exosuits for gait assistance and rehab after a stroke. I'm going to start with a quiz, and I expect the full gait analysis. What do you see in this video? Person struggling to walk. What you don't see in this video is that 4 years or several years before this video was taken, this individual had a stroke that damaged parts of her brain that control movement. And after her stroke, she underwent rehabilitation at some of the best rehabilitation hospitals in the world, located right here in Boston. But as you can see in this video, here she is several years later, and she is still struggling to walk. She needs a cane for assistance. Her gait is slow and asymmetric. By all counts, she's unstable. She's at high risk of falling, and she knows it. Balance, confidence, and self-efficacy is low after a stroke. And together, impaired mobility and reduced confidence lead to people post-stroke not walking very much in the everyday world. And over the long term, this leads to reduced health and quality of life. Now, I think a major reason why this is the daily reality for life after stroke is that the tools we have available for gait assistance and rehabilitation are inadequate. At its core, the problems that people post-stroke have trouble controlling movement. And in the current state of the art, in the current standard of care, what we do is we put them in a brace. To be very clear, instead of helping them control movement, we use bracing technology to eliminate certain movements altogether. But our team here at BU has a different solution in mind. To solve the motor control problem, we've developed wearable robots made of soft materials that interface with the biological musculature in a way that helps restore the control of movement. And over the last 5 years, we've combined clinical intuition with experimental biomechanics to guide the development of the exosuit technology, as well as deploy it across the post-stroke care continuum. And what we've learned from these studies is that when operated under the skilled supervision of a physical therapist in a clinical environment, these technologies can help people post-stroke walk with a better gait, and perhaps more importantly, walk faster and farther when walking with the exosuit powered on compared to powered off. But when we leave the safe clinical environment and use exosuits as tools for personal mobility in the everyday world, we need to better appreciate the neuroscience of an exosuit. What I mean by that is that exosuits don't do all the work of walking. They work in parallel with the user. Said another way, to walk successfully in an exosuit, the human and the machine have to cooperate. And when there's a mismatch between what the human is doing and what the exosuit's doing, or when the human is expecting something different from the exosuit, this leads to a loss of what we call automaticity, which we have documented as an increase in prefrontal cortex activity as people walk with a mismatched exosuit. And this is a major line of research in our lab. We asked the question, can we use portable functional neuroimaging technology to close the loop on the brain and avoid driving up the cognitive costs of walking, so that the same assistive forces used to help a person post-stroke walk to the mailbox leave them with the cognitive reserves that they need to not have to stop to think, wow, I'm walking to the mailbox. I want to make sure I thank my team and collaborators. Thank you all.